All right, so this homework video is going to go over section 3.7 in our textbook, going over the topic of optimization. Remember, optimization, we've got no new calculus to learn here. We're just finding maximums and minimums, but we got to consider domains. We have to think about real-world applications and kind of the formulas that we would need to start these problems. So first one that was most requested was 33, finding the minimum surface area. Okay, so minimum surface area means that this is going to be my primary equation because that's what I want to find the minimum of. We have a solid formed by adjoining two hemispheres. A hemisphere is half of a sphere. One hemisphere, two hemispheres to a right circular cylinder. The total volume of that solid is 14 cubic centimeters. Find the radius of the cylinder that produces the minimum surface area. So again, surface area is what we're going to try to minimize based on our restriction of volume. And we are looking to find the radius, r, that's going to produce that minimum. So the first thing I want to do is I want to start figuring out my surface area equation. So if I think about the surface area of this hemisphere, well, I've got a hemisphere up here and a hemisphere down here. So the surface area will be the same thing as the surface area of a sphere, which this is a formula from geometry that, yes, we would expect you to remember because we've now done a problem with it in calculus reviewing it. The next piece then of surface area is going to be the outside, or what we call the lateral area of this cylinder. We won't need the total surface area of a cylinder because we don't see these circles. If I was going to cover this in wrapping paper on the outside, I wouldn't have to wrap those circles. But I would have to wrap the soup label part, okay? And so if I think about this label on the outside, if I unwrapped it, I would get a rectangle, and its base would be the circumference of the circle times the height of this cylinder. So height being right here. So again, this comes from the lateral area of the cylinder. This comes from the hemisphere, and hemisphere makes one full sphere. All right, so then I'm going to create my helper equation for volume. Well, the volume of a cylinder is pi r squared h plus, again, I have one whole sphere, so the volume of that sphere is going to be 4/3 pi r cubed, and that needs to be equal to 14. This is the one that's going to get the calculus, but right now I've got r and I've got h that my surface area is dependent on, so I'm going to work with my helper equation to solve for h so that I can substitute h into my surface area. So pi r squared h is going to equal 14 minus 4/3 pi r cubed. I'm going to divide both sides by pi r squared. And so there's a couple different ways that you can write this. In my answer key, I chose to split up this fraction so I could cancel some things out. 14 pi r squared, sorry, 14 over pi r squared. And then in this situation, my pi's are going to cancel, and one of the r's is going to cancel. Two of the r's are going to cancel, so I'm going to have 4/3 r. So I'm going to go back over to my primary equation, the one that I actually want to do calculus on, and I'm going to substitute in my h value. So now my entire surface area is all dependent on the variable r. All right, well, I could take the derivative then from this moment right here, but I think it's probably better if I do a little bit of cleanup work to help cancel some things out. So surface area 4 pi r squared is going to stay. If I distribute this guy into here, I end up with 28. The pi's are going to cancel. One of the r's cancels, but I'm left with an r in the bottom still. So r to the negative first. If I distribute this 2 pi r into here, 2 times 4 is going to be 8/3 pi r squared. All right, well, collecting like terms, still haven't done any calculus yet. Surface area, these two are both pi r squareds, so I can combine those into 4 minus 8/3 is going to leave me with 4/3, okay, just doing a little bit of fraction work. Pi r squared plus 28 r to the negative first. So now I'm ready for the calculus step. I'm going to take the surface area's derivative, find the rate of change. So this is going to swing down 2 times 4/3 is 8/3. Pi r minus 28 r to the negative second. I want to consider where this thing is equal to 0 for a critical number, finding that maximum or minimum where it's going to happen. But also I need to consider where this may have been undefined. So when I rewrite this, if I look at this, when I think about this derivative, I might be undefined at 0 for the r. Well, that makes sense because if I don't have a radius, I wouldn't have a cylinder and I wouldn't have a sphere, so this whole problem would fall apart. So we know that r being 0 is going to be our lower bound if we think about doing our number line test. So I'm going to set up my number line. Surface area prime. Remember, you could do a second derivative test for extrema here, but the second derivative of this is going to be a little bit messier even. All right, so to solve this, I'm going to add the 28 over r squared to the other side. This is going to be 8 pi r over 3. A little cross multiplying and solving, right? I end up with r equals 1.495. So I chose to round, right? Because I'm going to end up taking a cubed root of pi in there. So r equals 1.495, put that on a number line, make sure that I actually am getting what I want to get, and I get a minus and a plus when I test into the first derivative. So I end up with a minimum surface area when r is equal to 1.495. And this one actually said you only needed to find r. So I think in my answer key, I went back and found that h was equal to 0 by plugging into that helper, but you don't actually need to. It just looks for the r value. And remember, 3 decimal places always. Or you could have kept things in terms of cubed roots of pi, but that just seems like a lot. All right, next one. Number 39, minimum cost. So this was one that I talked to my class about, that we wanted you to just try it and think about it. It's definitely a challenge problem. It says an offshore oil well is 2 kilometers off of the coast. So I'm going to give myself a coastline, and I'm going to put this oil well 2 kilometers off of the coast. Okay, and we know that our distance is going to meet up at the right angle from our geometry days. It says the refinery is 4 kilometers down the coast. So I'm going to put the refinery down here. This is going to be 4 kilometers. And then it says laying pipe in the ocean, because this is all water, right? If we're off in the coast, that's all water. Laying pipe down in the ocean is twice as expensive as putting it on land. Well, that makes sense, because if you put something underwater, you're going to have to dredge out more, and it's definitely going to be more expensive. So it says, what path should the pipe follow in order to minimize the cost? So there's a lot of ways that you can connect from the oil well to the refinery. You could go straight across, but now that's all underwater, and so that's really expensive. You could cut over and then down, but now that's 6 kilometers worth of materials. That's also pretty expensive. So what we are trying to do is figure out, where should I dig underwater versus where should I trudge underneath the land? So I'm trying to minimize that path. Well, I need to then figure out that path. So one way I could do that is I could say, all right, I want to put this blue part down X kilometers away, in which case this distance here becomes 4 minus X, right? Because these together have to make 4 kilometers. Then in my right triangle, if I wanted to know what this is right here, Pythagorean theorem would make this the square root of a squared plus b squared, right? It's the distance formula. So I am trying to minimize the cost of the blue and the red. Well, we got to figure out then that cost. I know that however much I dig under, I'm just going to use C for cost, save me a little bit of writing. I know however much I dig underwater is going to cost me twice as much as what I put on land. So it's going to be 2 times as much to dig underwater as it is to just dig under land. All right, well, I'm trying to figure out where should X be, right? X is this guy right here. How far along before I start digging underground? So I want to take the derivative here. C prime equals 2 times 1/2, leave the inside alone, drop the power times the derivative of the inside with the chain rule, plus the derivative of 4 is 0, derivative of negative x is going to be -1. All right, I'm going to set that cost equal to 0 and also consider where it may have been undefined. So cleaning all this up, 1/2 and 2 goes away, but I still have a 2x over the square root of x squared plus 4 minus 1. Well, the square root of x squared plus 4 is always going to be a positive number. There's no way to get 0 out of that. So I don't have any undefined values, but I will add this 1 over to the other side. I end up with the square root of x squared plus 4 is equal to 2x. I'm going to square both sides. And if I continue over, I'm going to move this to the other side. I'm going to end up with 4 equals 3x squared. So x equals plus or minus the square root of 4 over 3. Well, if I put that on a number line, I do in fact end up with a minimum, right? X at the very least could be 0. At the most, x could be 4 because that's where I could move, right? 0 would be if I put it underwater to the right angle and then under land down to the refinery. The 4 would be if I just, 4 would be if I did that. 0 would be if I just went across straight to the refinery, but we know that wouldn't be the best. So in terms of plugging stuff in, I do end up with a minimum at the square root of 4 over 3. It wouldn't make sense to have a negative number for our domain here. So in thinking about this, the reason my answer key says 2 root 3 over 3 is because I just rationalized. So x is the square root of 4 over the square root of 3, which is really 2 over root 3, which I simplified to be 2 root 3 over 3, and that would be kilometers. So what that means is, I'm going to erase some other things on this picture so we can see better. This distance right here would have been 2 root 3 over 3. Okay, and that's where I should then dig over underwater until that point and then start digging under land. All right, I'm going to go ahead and make a second video to talk about the last 2 problems that you guys had requested.